గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్ గారు. What was the attendance like yesterday?
Yesterday morning session, it went up to 120 plus. Some are joining through YouTube live streams.
సో దానికి మనకి కౌంట్ లేదు కదా.
వాళ్ళ నుంచి మనకి ఫీడ్బ్యాక్ ఫామ్ కానీ లేకపోతే మెయిల్ కానీ పెడుతున్నారు సార్ అటెండ్ అయ్యామని. దీంట్లో అయితే మోర్ దెన్ 100 నెంబర్ వస్తుంది మార్నింగ్.
ఇప్పుడు దానికి లింక్ ఎలా దొరుకుతుంది మనకి?
యూట్యూబ్ సార్. యూట్యూబ్ పార్టిసిపెంట్స్ అందరూ పెట్టాం సార్.
అచ్చా, మీరు పెట్టారా?
డే వైజ్ అంటే స్పీకర్స్ ఓన్లీ గూగుల్ మీట్ పెట్టాం సార్. పార్టిసిపెంట్స్ కి ఇది అది కూడా పెట్టారు. ఒకవేళ ఫుల్ అయిపోతే దాంట్లో షిఫ్ట్ అవుతారని అది కూడా డే వైజ్ లింక్స్ ఇచ్చాం.
ఓకే, గుడ్ గుడ్. లాస్ట్ కోర్స్ కి ఓవరాల్ రెస్పాన్స్ ఎలా ఉంది? లాస్ట్ ఎఫ్డిపికి ప్రీవియస్ ఎఫ్డిపికి ఓవరాల్ రెస్పాన్స్
బాగుంది సార్. మొత్తం నేను మీకు అది సమ్మరీ షీట్ పెడతాను సార్.
ఎనీవే ఇట్ ఈస్ టూ మచ్ వర్క్ ఫర్ యూ బికాస్ కాన్ఫరెన్స్ తర్వాత FDP1 FDP2 we know it's not a small thing.
IGC వల్ల I could not organize this FDP.
No, but still whatever
వల్ల అంత జనవరి టు మార్చ్ లో ఇంకా
అవును. మీకు ఎంటెక్ లో ఎంతమంది ఉన్నారు స్టూడెంట్స్?
ఎంటెక్ 18 ఉన్నారు.
18 ఉన్నారు. అంటే దట్ ఫుల్ టైమ్ అండ్ పార్ట్ టైం?
అంటే సాయిల్ మెకానిక్స్ లో పార్ట్ టైం లేదు సార్. ఓన్లీ ఫుల్ టైం.
లేదా? మిగతా వాటిలో ఉందా పార్ట్ టైం?
పార్ట్ టైం ఓన్లీ ఈవినింగ్ CTPM అని ఉంది సార్. కన్స్ట్రక్షన్ టెక్నాలజీ అండ్ ప్రాజెక్ట్ మేనేజ్మెంట్. వర్కింగ్ ప్రొఫెషనల్స్ వాళ్ళకి ఈవినింగ్ 5:30 to 10 అవుతాయి సార్ క్లాసెస్. స్ట్రక్చర్స్ ఒకటి ఉంది సార్ ఈవినింగ్.
మీరు ఇప్పుడు సాయిల్ మెకానిక్స్ ఫ్యాకల్టీ, మీరు ఇంకో సత్యాన్ని గారు, ఆ లేడీ ఒక అన్నారు, ఆవిడ ముగ్గురేనా?
అంతేనండి. ఆవిడేమో ఉమెన్స్ కాలేజీకి మా AU కాలేజ్ ఆఫ్ ఇంజనీరింగ్ ఫర్ ఉమెన్ ఒకటి స్టార్ట్ అయింది కదా సార్. సో అక్కడ హెడ్ కింద అటు వెళ్ళిందండి. ఇక్కడ లేదండి, తను లేదు. అంటే కోర్సెస్ చెప్తుంది వచ్చి ఎంటెక్ని, ఫుల్ టైమ్ అవైలబిలిటీ లేదు. కాకపోతే మాకు ఇన్స్పైర్ ఫెలోస్ ఉన్నారండి. ఇన్స్పైర్ ఫెలోస్ వాళ్ళని కొంత యూజ్ చేస్తాం, కొంత ఇన్వాల్వ్ అవుతారు వాళ్ళు కూడా. వాళ్ళు విక్టోరియా స్టూడెంట్స్ కాబట్టి వాళ్ళు కూడా కొంచెం లోడ్ ఇస్తాం సార్. టీచింగ్ 2 ఉన్నారు సార్.
ఇన్స్పైర్ ఫెలోస్ అంటే వాళ్ళు దేర్ స్టూడెంట్స్ ఓన్లీ, సీనియర్ స్టూడెంట్సా లేకపోతే ఫ్యాకల్టీ?
ఎంటెక్ టాపర్స్ కి DST ప్రోగ్రామ్ ఉంది సార్. సో దాంట్లో వాళ్ళు రీసెర్చ్ పర్సూ చేయడానికి DST సపోర్ట్ చేస్తుంది వాళ్ళకి. మంచి స్కీమ్ సార్ అది. వాళ్ళకంతా కూడా వాళ్ళ రీసెర్చ్ వర్క్ కి వాళ్ళు ఏమన్నా అటెండ్ అవ్వడానికి అన్నిటికి కూడా మంత్లీ కూడా రీజనబుల్ అమౌంట్ ఇస్తుంది. మన సాయిబాబా రెడ్డి గారు అబ్బాయి కూడా ఇక్కడ ఉన్నాడు. రాకేష్ రెడ్డి కూడా ఇక్కడ నా దగ్గరే చేరాడు.
ఇప్పుడు ఆయన ఎక్కడున్నారు?
ఆయన హైదరాబాద్ లో విద్యా భారతి ఏదో ఉంది సార్. ఏదో ఒక కాలేజీలో చేరారు సార్. డీన్ కింద డైరెక్టర్ కింద ఉన్నారు సార్. అంటే వి సీరియస్ ఉన్నారు కదా, అన్ని ఇంకా తేలలేదు కదా సార్. ఇంకా తెలంగాణ టైం బీయింగ్ చేయాలి.
మీరేం రేసలేరు ఎక్కడనా?
ఇంకా ప్రస్తుతం ట్రై చేయట్లేదు సార్. ఎకడమిక్ ఇలా రీసెర్చ్ ఇదే నాకు ఇష్టం సార్. ప్రస్తుతానికి అయితే ఇంకేమీ లేదు సార్.
అంటే దట్ ఈస్ ఎ డిఫరెంట్ లైన్ యాక్చువల్గా టోటలీ
సార్.
Yeah, Karthikeyan wants to ask some question. Yeah, Karthikeyan.
Sir.
Yes. Hello, sir. Good morning.
Good morning.
Yes, sir. Sir, actually, yesterday I had mentioned about the saturated clay. The saturated clay, we perform only like either UU or UCS. You have mentioned. So, can you just elaborate that one, sir? I have two more questions, sir. Can I will just ask one by one.
Are they related to this or
separate? No, not related to this. No, separate.
Bro, if you take a clay soil, saturated clay soil, okay, that means below the water table. Naturally, we are interested in finding out its bearing capacity under the immediate loading conditions. Kada? The moment you are placing the load on that now, what is bearing capacity? So that means immediate means actually in the field it may take a week also. And we talk of immediate, but it may take a week also. So once you are placing such a load of the foundation on the soil, there is excess forward pressure generation because the load you are applying now. Okay, and if that is so now, there is no chance for this excess forward pressure to get dissipated. So it becomes an undrained case. So undrained case naturally you are able to get by the unconfined compressive strength itself. You can also do UU test anyway. I have shown you the result. I can show you again also today. And in the undrained, uncontrolled undrained test now, you are not going to get any other phi or something like that. It will be phi 0 or what you call phi UU 0, and then there is a cohesion intercept. So the cohesion intercept comes to you even by the UCS also for this material. And you will also realize in the course of time in today's lectures also, I mean, which you are already knowing anyway, this value of C is most essential for us because NC is a constant value essentially. Even the variations with respect to many things now, it will be at best 9 or something that the NC value. So, and the bearing capacity is not influenced by the width or depth of the foundation also by and large. If that is so now, the C value is most important for us now. So this is invariably the case. The undrained case is invariably the case. That is homogeneous saturated clay. Essentially means below the groundwater level is going to give us only the relevant strength for immediate distance. Now, if you talk of long-term stability, obviously long-term the soil is going to consolidate it. Okay, in which case you will get a phi value and no C is there. I mean that means you conduct a CU bar test. Of course, CD also can do, but CD will take much longer time. But then if you conduct a consolidated undrained test actually. With forward pressure measurement, what is it we are going to get? We are going to get the phi is some value and C0. So you can use the phi actually and then also determine the bearing capacity. But you can also understand by and large, the soil is better soil now because it is now consolidated and the loads are applied now, which may take its own time. It may take years for this to happen now. So that is what I was trying to say, but I will reinforce it by showing you that what I shown you the animated this one, and also when you talk about bearing capacity, we discuss that also again. Okay, any other clarification required on this?
Yeah, no, not this one, sir.
No, not clear on this now.
Yes, it is clear, sir. Thank you.
Okay.
And in the DCPT, you mentioned that by DCPT, we can perform so many estimations like void ratio and CBR. So
no, I didn't say that. I didn't say this. DCPT just gives you the n values, let us say, continuously. In a way.
Yeah.
What I said, of course, was just doing SPT, we're expecting a lot of things to happen from that value itself. Is it right or not is what I said questioned. Because we should remember that we got a single value So based upon, if you just let us say value is 20, you're just assuming the character value is 20. Now, how correct it is, how it is representative of the depth and width of the entire area we are looking at actually, is what we have to question, because we are determining the density density, we are determining directly the angular friction. That means we are determining obviously the bearing capacity. Many things we are determining, type of foundation, 100 things are determined based upon that now. And people, I didn't show correlations, they're available in standard books now. There are many correlations with to the N value. So if you think that we are going to use the correlations, the test has to be done very nearly perfectly. And also we have to apply the corrections much more than the what you call diagnostic correction or button correction. These are two minimum things we are trying to do. But for this, very good clarification is given in the book Bowles actually, which at the end he makes a paragraph also clearly saying that these days not required to do all this kind of correction, because whether you do the correction or not is immaterial. You have to only do the energy correction. That N70 is the value which you are using for the correlations the table have given you, is it not? So that means that value is the corrected value for all these things now. And if we think that it's only density and what we call the overburden correction, that is not sufficient. In fact, there's a man required also. So that is a question of judgment. I will show you the particular paragraph also in the our code 6403, I think, for bearing capacity. I don't remember the exact number. But the point I'm trying to say is that now, even there also it says, even the theories you are going to use with judgment now. I'm going to show that aspect from that now. So both that and N values are very important for us now. So in fact, Professor Satyanarayana Reddy titled this also, IS 6403 method for bearing capacity, relative merits and limitations. Actually, we should really focus on that also, which I am trying to do in a limited way because time is not so much now.
Okay, sir. Okay. Sir. Yes, sir. Sir.
Karthikeyan, we can discuss later because it is time to start the session. At the end of the session, you can again interact. Okay.
Where are you from, Karthikeyan? Hello.
Sorry, sir. Yeah, yes, sir. Sir, actually, I am from. I am working in Mauritius, sir, in a geotechnical consultancy. Basically, I am from Tamil Nadu. I did my MTech in MTech Engineering Geology in IIT Dhanbad. Now it is IIT. Before it was ISM Dhanbad. Now
so you're in geology. That's why you got all these jobs. Good. Thank you. Then we'll hear from Satyanarayana Reddy.
Yes, sir. Thank you, sir. Please.
So good morning to all the participants. I welcome you all to the second day technical sessions of faculty development program. So in the morning session, now we have a lecture on bearing capacity theories of Meyerhoff, Skempton, Hansen, Vasic, and Balla. And after that, we'll have a presentation on IS 6403, method for evaluation of bearing capacity of soils. So Professor G. Rao sir will in detail explain about merits and demerits of each of the theories, including our IS 6403 method. Now I request Professor G. Rao sir to deliver his lecture. Please, sir.
Okay. Good morning and thank you, Professor Satyanarayana. Is the screen visible?
Yes, sir.
Thank you, and I hope I am audible also.
Yes, sir.
Good morning, everyone. The topic, of course, we are going to choose is the practice of foundation engineering. We are going to focus on the relative, what do you call, the parameters which are going to influence the so-called bearing capacity in the field. How a practitioner looks at it. That is what I am going to review. But before that, I thought I will also conclude what I have done yesterday. Let me just go back to my own original slides actually and show you What are the aspects which we are going to focus? Because the parameters which are going to take off, the strength parameters which are considering are going to be very important for us to remember, and then also obtain the parameters rationally. I'm assuming that all of you are conversant with the triaxial testing, which you have done in your masters. And if you have not done so, I think I advise you, all of you, to really get some experience in trying to do this, because this is going to be one of the most important things we need actually for determining the strength parameters in a nearly perfect way in every conceivable aspect of design. Geotechnical design, we say that whether it's going to be slopes, or it's going to be foundations, there's going to be defoundations, there's going to be earth pressures. Everywhere we require these test results actually. Under what conditions? So one thing we said in the beginning was that the soil as such doesn't have a unique stress relationship. It doesn't have unique value of strength, unlike the cement or steel, because it is controlled by the external conditions, the boundary conditions, and also the presence of water creates certain issues of permeability, of pore water by generation, or pore water by dissipation. So to simulate these conditions, we have this triaxial test in which we obtain a sample from the field, so-called undisturbed sample, and assemble it in a triaxial test apparatus and apply a confining pressure. Now, the first thing we are going to look at is what kind of confining pressure we are going to apply in this now. I mean, the cell pressure is confining pressure. We know that in the beginning it's going to be an isotropic pressure application. So we have the sigma 1, sigma 2, sigma 3. We have the sigma 1, sigma 2, sigma 3. But then naturally, in the beginning, in the first stage of the test now, we are going to apply confining pressure. So that means all the principal pressures are going to be equal. They're going to be the same actually in the beginning, the first stage 1 actually. Now, what are these values representing actually? One, of course, we are going to conduct the test at 3 different confinement pressures at least. Now, these confinement pressures which are going to apply, or cell pressure going to apply, should be somewhat related to the field situation at which you have taken the specimen or you got the sample. Supposing you have taken the sample at 10 meter overburden, 12 meter depth actually. So the 10 meter overburden, effective overburden pressure, we are going to apply on this sample, because that is what is going to bring it back to the condition at which it was there existing. Then we are going to apply the loads of the structure actually. So the range of pressures we are going to apply should reflect these extra loads which are going to have. So we'll have the 3 confinement pressures, at least with the minimum overburden pressure we had already, and then maybe two more pressures which are almost double than, suppose you say 100 kPa is the pressure at which we got the sample, the overburden pressure, and maybe we'll do 200 and 400 kPa is what we're going to apply. So that's the first thing. So first stage is we are applying the confining pressure equivalent to the effective overburden pressure. Mind you that this is effective overburden pressure is only the vertical stress actually in the field. What about the lateral stress now? The lateral pressure is not necessarily going to be same as the vertical overburden pressure, and that means we are already making an estimate of things. We are just assuming that the specimen in the field condition is under an isotropic condition. It is not going to be isotropic pressure conditions. Otherwise, of course, we have to calculate what is horizontal pressure, what is the horizontal stress, let us say, on the specimen, and which is more tedious. That means, unless you do the test, we can't know these conditions. So the first approximation we are going to do in the test itself, we are going to be that we apply a pressure equivalent to the effective overburden pressure. And then, of course, more and more so. So when you're applying this now, what we said was that during this stage 1 of the test now, naturally, we can allow, when after application of the pressure, naturally, we are going to have development of the excess pore pressure within the specimen. And whether we are going to dissipate the pressure or not is our choice now. So in the second stage now, after whatever we wanted to do with this now, allow the dissipation of pore water pressure or keep it there only, the second phase of the test, second stage of the test is going to be applying a deviator stress. That means we are going to apply an additional axial stress on the specimen, obviously in a certain way, and we reach the failure stage. So that is what we are going to look at basically. So when trying to do that now, we defined last time itself that we are going to have 3 combinations actually. The 4th combination is not feasible. You can think why the 4th combination is not possible. But then, so in the first stage now, we are going to have this undrained condition. That means pore pressure is still there, exit pore pressure is still there. And the second stage is going to be that we are not going to allow also consolidation in the first case, which I got here now. So this is what we are referring to as a undrained, unconsolidated test actually. Results of which I have shown you yesterday, but I will also show again. So that means till the end of the test actually, the pore pressures which are developed during the first phase 1 and the phase 2 here are going to remain there only. So this is a totally undrained case. Obviously, this is going to come up only in a homogeneous saturated clay. Okay, that's very clear on this now. And obviously, we can't easily make a specimen of sand in the laboratory. So this applies essentially clay conditions. The second kind of test is, of course, what we are going to do in the first phase. We are going to first apply the cell pressure and then allow the excess pore pressure to be dissipated. So the sample is consolidated. We give adequate time for that. And then after that, now we are going to apply the additional axial stress under undrained stage, under undrained condition. What we mean by this now? We are going to close the burette or the volume change measurement device now and allow the pore pressure to be dissipate pore pressure, which is going to be developed under in the second phase, and we may choose to measure the pore pressure or we may not measure the pore pressure. So it becomes a CU test when you're not measuring pore pressure. It becomes a CU bar test when we are going to measure pore pressure. Okay, so by this process now, what is going to happen now? At the end of the first phase now, there is no pore pressure. The pore pressure only comes up in the second phase of the test now. That is going to be very important for us to keep in mind actually. And in the last phase actually, it is going to be, we are going to allow the drainage to occur continuously in both phase 1 and phase 2 also. It becomes a CD, consolidated drain test. So that is what we are going to look at actually. So this is what I wanted to say. The second test here is defined here more clearly. Consolidated undrained test with pore pressure measurement is CU bar. So when once you say that we are going to measure pore pressure, or when you say that in this third test the pore pressure is not there at all, so both are going to give us actually the effective stress strength parameters about which we talked yesterday. We will again recap. So we are going to use a Mohr Coulomb concept. I hope you are familiar with this now. So we have a linear relationship between sigma and tau. And in the relationship now, what is it we're defining? We're defining this the slope of this line actually by an equation tau f is equal to c plus sigma tan phi. C becomes the intercept on the vertical axis, the tau axis, and then phi is the angle here which we are measuring, and then sigma is the obviously the pressure we are applying or the stress we got now. Now, what I mentioned yesterday, what we repeat again is that these are only strength parameters. This is no way of reflection. The actual cohesion it may occur, it may happen in the clay. That means it's going to stick to your hands, so there is a cohesion, and then phi is not there in the clay. It's not meaningful. These parameters are strength parameters, and we determine them under the different drainage conditions which you already thought now. So we should relate this to the friction between sand particles or the adhesion between the clay particles. It is only strength parameters, and we determine them in the what we call as the total stress conditions or in the effect stress conditions. That is what we are going to remember. Remember, I think this is most important criteria. This is what I mentioned here again very clearly for you to note down that C and phi are measures of shear strength designated as strength parameters, either they are effective strength parameters or total strength parameters. Obviously, if you got strength higher, naturally the values, that means if the values of C and phi are higher, obviously it means that it's going to have higher shear strength. That is obvious. So the first case we determine what we call as the saturated clay, let us say. In this case now, what we are going to do, we are going to initially assemble a sample, let us say at a confined pressure of 50 kilopascals, and conduct the test actually, and plot this failure value of sigma also here now, and we get a circle like this. We can conduct the second test at a confining pressure of cell pressure of 100 kilopascals, and then we get another circle like this. And then of course we can also conduct a third test at 200 kilopascals. So this is going to be the result of this now. And mind you, in this test now, which is EU test, actually, we are not measuring pore pressures. Everything we're measuring is going to be in total stress conditions. So in these total stress conditions, obviously, we plot a common tangent between all the circles. This common tangent is the failure envelope, we call it now. And what is it we're going to get now? First thing is horizontal. So the value of phi is really 0. And then there's intercept, actually, on the y-axis, on the shear axis. So intercept is going to be given as sigma, as C. Now, the second thing which we have thought also was that what is going to condition or what is going to be the most accurate actually when we conduct a unconfined compression test on the same kind of clay. So when once you have applied no confinement, that means no cell pressure 0, that means you are going to test at sigma is equal to 0. So when you conduct such test now, it will be surprising that we have the circle of the same diameter, which means that the intercept we are going to get now is going to be giving you simply a value of Cu, which is going to be same in all the cases actually. So that is what we are going to remember always. So when we conduct a test on this now, it's going to be naturally giving a phi value of 0 and C is a positive. What we also mentioned is that we can conduct a similar kind of test in the field by using a vane shear test also. Vane shear test also is done a few minutes now. We rotate the vanes actually, and we can find out the strength. And there also, we are doing either laboratory or of course in the field also. What's going to happen? We're not going to do any more consolidation. Whatever is there in the field, we are going to do that only. We're going to run the test in the field means in the natural condition we're going to do. That means the effective over pressure remains whatever it was there. And then of course the test is done a few minutes now. There's no chance for any excess power pressure to dissipate now. So that also is fully what we call as giving you the value of C under the undrained conditions. So that is undrained cohesion now. So this can only be, as I said, Robertson parameters actually. So this is very clear for us now. So for saturated NC clays, and meant normally considered clays, phi is equal to 0, and tau peak is going to be Cu. So that is what we know. So this, there are also a way of trying to express this. Sometimes, you know, in the early generation, people used to call this value of this as S actually, capital S. So that also we use it when you go to bearing capacity. So that is very important for us. Now on the same kind of soil now, if you conduct a test actually, if you conduct similar kind of test, but then a CU bar test actually. So when you conduct a CU bar test, what we mean is actually first phase is consolidated, second phase undrained. That means in the second phase there's no there is a power pressure generated, but it's measured actually. So when you really plot this under reference conditions, what is it we find? We find circles of really of different diameter. Why it's happening now? In this case, let us say we had a confined pressure 200 kilopascals, and then during the test there is power pressure generation. But before the test itself, before the phase 1 is complete, the sample got consolidated under 200 kilopascals. And here at 100 kilopascals, here at 50 kilopascals. So that's why with higher confined pressure applying, the consolidation is over the first phase itself. Second phase only excess power pressure generation now. So we can always plot these values perfectly, and then we find that the common tangent of this is going to be a line. Is again the Mohr-Kleffel is going to be a line. So in this line now, we can always now get that this value is going to be, that means the intercept here is going to be nearly 0. For the same soil, same clay soil. So what we find is that there is a phi now. So can't we say that the clay has got now, there is no cohesion and there is a phi. So we should not think that clay doesn't have the friction things like this, because C and phi are only expressing the length parameters. This is what we have to remember. Okay, in the same way, we can also plot the tortoise plots. There's no problem on that, but it is going different now. So this is what we are going to remember now. For the first EU, we have got Cu and phi U 0. And then for the Cu, obviously, we just see what is that now. For the CD test now, everything is drained only. There's no power pressure there. There's no excess power pressure there. So we are going to get only effective system parameters called C prime and phi prime. This is very important for us now. We'll repeat. Glandular soils will not have any cohesion. C is 0 and C dash is 0. Inconsolidated inclined test in terms of dollar stress now phi is 0. And then for normal consolidated clays, C prime is 0 and C is also equal to 0. What we should remember is that in our huge country now, we got different kind of soils now. Each one of you actually should have some exposure to the properties of the soils which you got in a region, and you should make an opportunity for bringing the samples in laboratory. Just to yourself, whether you get consumers or not, you should try to do this for the soils all around you for different depths and different variations, and then you get a physical feel of what we're trying to talk. So finally, in the beginning, people used to think that we will just drill a hole in the ground, send the soil samples obtained from the hole to a laboratory with the standardized apparatus served by, let us say, what people call as conscious human automation. That means, they are doing the test perfectly. There's no problem of doing it now. But then we just collect the figures introduce them into equations, and complete the result now. Unfortunately, as Carl Razagi, our father says, unfortunately, soils are made by nature and not by man, and the products of nature are always complex. So just merely doing the test mechanically and putting these values in the equations will not make any sense at all, actually, because there are several things between the cup and the lip, actually. For example, I can show many instances wherein things had perceived in a different way. It could be our own analysis of things, actually. It could be our own way of thinking. It could be we have to keep our eyes and ears open of the performance of different kind of structures in our area, and about which we'll talk more as we go further. So when you come to, from these values, we are trying to obtain what is the kind of load we are going to have, what we can have of a structure, what we call a foundation structure of different size, different dimensions, different depths. And we have very crudely seen that when the load is distributed just very near the bottom of the what you call column, or very near the surface, naturally it's called a shallow foundation. We'll have definitions of that anyway clearly. But as a rule now, the shallow foundation is going to be more economical. For example, if some of you must have gone to IIT Delhi, all the structures, some of the major structures up to 7th story were all on shallow foundation only. Today, you can't think of 7th story structure on a shallow foundation, but that is the situation. I think nowhere in IIT we have a deep foundation. They are all just shallow foundations only, though major the structures. The other kind of thing is I want to share with you. When I went there, of course, in 75, there was in the main institute area, there was a huge car park actually. Car park obviously is well paved and things like this now. After some time, probably in the early 80s now, the institute decided that we are going to have a library building there, a 4-story library building. But every building is always heavier than a normal residential building because the books are very heavy. The stacks of books is going to make it very heavy. So they said we are going to have construction here. So please go ahead with the investigation. That's what the institute wanted us to do. So when we were investigating this now, obviously we went to 30-40 meter height. And then we did it all the 4 corners. We did the center of that area also. The building itself could be 50 by 50 meters, very crudely. But then we found that, there is a kind of, we can say a bowl. That means above this bowl, let us say, we have loose soil. And below this bowl is actually, you can say, a more stronger or more SPT and more higher strength parameters, lesser consolidation, things like this. Now we were surprised. How come this bowl is coming now? That means the corners it's always better. At the center it is poor. I said it's all level ground, But then we had occasion to talk to the earlier watchmen who were there watching this. So when we interacted with them, they said, sir, actually this was a pond actually. This area was a pond. This pond was filled up and made into a car park. So long as the loading of car park is there, naturally no settlement, no problem of the car park. But once we started investigating now, we know that it's all filled up ground actually. So this is the most important aspect of our investigation, and then a decision on what kind of foundation, because you have to know what is the natural soil depth like actually. That is most important, because most of the structures today by the government, what the contractors do, they first level the ground to begin with. So that means you lost sight of where is working ground now. So that means only by investigation you are able to know what is natural ground now, because natural ground is always going to be stronger than filled up material. This is something we have to do that now. So before we take a call on what kind of foundation we are going to have, we ought to know what is the depth of the natural strata which was there and how much is filled or how much is cut actually. So as a general rule, we always consider when the shallow foundations are not giving a satisfied design, naturally we are going to do that. So in a shallow foundation, obviously we look at, the students look at some structure like this only, but then it could be rectangular foundation, it could be horizontal foundation, it could be strap also, obviously it could be mat foundation. For each one of them, we got different kind of parameters now. For example, in this case now, relatively high ratio of soil resistance to structural loads, because the area is more now, the resistance, the bearing capacity is going to be, not bearing load, is allowable bearing load is going to be more actually. The area is more. And here, we are going to use it now. When the actual bearing capacity of the soil is smaller now, we adopt naturally, a much more wider foundation, you can say, or a raft or mat, what you can call it now. Now, these conditions will come out actually because resistance space now, but they're also common now. For foundation of tanks, we have ring foundation also. So the kind of structure and of course the ground conditions, availability of the land for you next to your border actually, next to your boundary, is going to influence the kind of foundation. So though we often look at this kind of isolated footing, or let us say continuous footing like our compound wall or anything else like this is going to be common things, but then these so-called uncommon things are also going to be very important for us, and sometimes we need to use our judgment in deciding what is the actual bearing capacity like now. So the foundation choice is going to be obviously by the surface of the soil, and obviously groundwater conditions, and also structural requirements. All the three are important. Now, the one point we have to remember is, yes, we can know the subsurface soil conditions by doing investigation, so also the groundwater conditions. But the structural consequences are equally important for us. That means before you give a decision on the recommended load which the soil can take at different depths and different depths of foundation, it is important for us to understand what the architect or what the designer of building is going to plan. What is it he had in mind? Has it got individual footings, or has it got, let us say, continuous footings, or has it got a raft in mind, or has it got a deep foundation in mind now? For example, we may think, like we have done in IT Delhi, that even the 7-story building can be on, let us say, on shallow foundation. But the other way around, the architect or designer of the building can think that he's got something else in mind. He has got deep foundation in mind. So when once you got deep foundation in mind, when I'm having only shallow foundation in mind, my depth will be restricted to the conditions I mentioned earlier, maybe 1.5 times B. But if you got deeper foundation, obviously we need to go much deeper than this now. What is more important for us is now, when once the actual user of your data is going to decide upon deep foundation, much against your wishes of shallow foundation, are we going to go back to the site and do investigation again? No. So that's what I said. We have to get to know the mind of the architect or client. We have to also know the structural requirements, how close the spacing of the columns and things like that. Are there any heavier columns than what we normally think of, as I mentioned, the staircases or the lifts and things like this now? So these ought to be known well before you do the investigation also, and definitely when you are going to give us the so-called allowable bearing pressure. And we know that the three things which are going to be most important for a foundation, successful foundation, one, of course, from a pure soil mechanics viewpoint, the bearing capacity and the settlement. There are two things which you all do. But the third, the number of factors, these are called nebulous factors. For example, if you are looking at a structure, like a pump house, something like that now, next to a canal or next to a river or something like that now, or a pond, naturally, sometimes cover may become important. If you don't consider score now, naturally, you are gone. In the same way now, there are many things which are going to there. Maybe there are, you can say, what you call godowns with a very, like a cold storage, let us say. So obviously, the cold storage is going to also completely change the kind of soil profile. Change means actually it's going to frozen now. So we got a different kind of thing. When we're going to open it now, it's going to be different kind of issues. So the point I'm trying to say is that there are the third element is nebulous now. Yes, in all our books now, we got a lot of conditions. I will also show you the conditions given by our IS codes now. But this list is never complete unless you are able to understand the total situation in and around the proposed structure and the experience of the neighborhood actually. This is going to be sometimes more crucial than determining your bearing capacity. So when determining the bearing capacity, I like this this part of picture. I have taken this from the book, classical book by Professor Lenartz, J. Lenartz, actually from Purdue University. And so in his book, he has written this chapter on shallow foundations. And what is it he's trying to say? First, we'll take up a small plate, let us say, which is a model bomb and model, you can say, foundation, shallow foundation. And he has conducted a plate load test on this. So in this plate load test result now, we got a linear portion initially. That means the relation between the load and settlement or vertical deformation is going to be almost linear now. Beyond some level, it is actually going to be changing faster. And then, of course, afterwards, it may become a straight line actually. So when you look at a plate load test result like this now, what is it you will say? You will say that, okay, extend this line backwards and extend this line also forward. And then wherever these two dotted lines meet, we say that that is the theoretical point of failure. So when you are trying to look at that actually, so what is it we are looking at it? This is the theoretical point of failure. And we do all our calculations based upon this, but we actually forget what is happening on the soil strata, which is depicted very well now. So in the beginning, when we are under the linear conditions here now, initially the entire foundation or the plate we are going to do now is actually moving down vertically. You can say it is settling vertically. So during its process of settlement now, slowly, what's going to happen now? This part of it, the bottom of the foundation, is going to develop a near conical shape actually. That means this part of the soil is going to stick to the bottom of the foundation, and this wedge is actually trying to move down now. And when it's trying to move down, initially it will actually bulge. It means it will push the soil away slightly on both sides, but it's a concentric load, mind you. We're applying a concentric load. And then, of course, after some time, that means when we have increase in load, actually, this entire failure surface is moving upwards, actually, and then resulting in a bulge outside, actually. Now, when this is happening now, the initial portion, which you got settling, and some cracking, local cracking around the foundation is the linear portion. Once this wedge is being formed, and then naturally the bulging is also going to form now, you will find that is a non-linear portion now. And once it's completely formed, actually, that means the entire load is taken by the soil of whole soil anyway, but outward movement, bulging actually means that it is actually failed. What means is that we are going to have a rapid downward movement and shear failure actually. So till the local cracking occurs, it is linear, and local cracking, naturally this is a curved portion, and beyond that it may become vertically downward or of course some inclination now. So this is going to result in what we call as shear failure. So we should understand the stages of this, because we always talk of that there's a bulging anyway. In many cases we feel now, even for embankments, I watch this actually. But embankments of soils, it's very common phenomenon. For example, Visakhapatnam itself now, when we are doing the NTPC major work actually, they were putting a pipeline from the sea for the cooling water actually, the sea water. And you find that the entire embankment was moving down, which is noticed anyway, but both sides now, we find that there's a bulge very clearly seen actually. We find this in normal cases, observed like this in a road, also in, it's a Guntur, and most of you can also watch this actually. And that means that this load is going to be causing failure. And it's imminent failure. What it means really that you can't place any more load on this, because any more load means the relation between these two things are disproportionately increasing. The settlement is increasing disproportionately with increase in load now. Earlier it was of course linear. Now the relation between the load and settlement beyond this line, beyond this value, is going to be disproportionately increasing. That means causing total collapse of the structure actually. So distortion and downward movement, these are important. So what we are trying to look at is that the shape of this zone. The shape of the zone has been investigated by many people into different kind of rock spiral and things like this now. And then people have also assumed a different shape of this conical portion now. And then people have also considered the surcharge over this now, which we'll discuss now. But one thing which is also evident is all these phenomena are occurring when the load we are applying on this is concentric. Once this becomes, say, some kind of movement, or when it becomes inclined load now, what's going to happen now? It is going to tilt, and so we are only going to have only one shear zone. There are twin shear zones here for constant loading now. So the moment some kind of inclined load is going to come or moment is going to come, it may also happen that only one side only the shear zone is going to form now, and that means that whatever capacity you are going to have for the load bearing is becoming half only, because you have this one shear zone only. So that is a very dangerous situation. And this may happen obviously when you got foundation slopes also. It may happen over this also. Our attempt should be to somehow manage this in different ways, in trying to take the inclined load in different way, and also try to see how this is going to prevent it. So that becomes a separate exercise by itself now. We should also try to inform ourselves that this is a natural kind of situation. Another situation which you have to remember also is that sometimes it may happen that this base of the foundation itself is tilted. Sometimes it may happen that the ground also is inclined actually. Now the classical equations by Carl Terzaghi or further mechanics don't include all the things. Yes, it has got some rectification measures, and the advances in Bent theories are all coming out because of this. So in the first assumptions he made actually is of course a punching theory, punching of plates, actual metallic plates, and that he modified. Carl Terzaghi modified this actually. And what is the final result of all this analysis is going to be that this wedge which is going to form, which is punching into the ground. Then this wedge we are talking about is punching ground now is assisted by the friction around this wedge portion, and also by the vertical component of the earth pressure which is going to be generated by this entire zone, what we assumed as a failure zone actually. And all the calculations which people have done, as mentioned by Professor Sajana Tiger also, is by Mayerhoff, by Scampton, by Vasek, by Balla, by Hansen, and many other researchers actually have worked out different models of the shape and different models of how this is acting. And people have also applied these models actually in order to find out the bearing capacities of only piles foundations also. So that means these are generic theories to begin with now. So it is clear that this zone actually, this failure zone divided into two zones actually. One is radial shear zone, that means this is radial shear zone, and then a linear shear zone. So linearly there is no problem at all, but the shape of this radial shear zone is what we can imagine, and different shapes can be imagined now. We can imagine actually this line, this inclination to be different. We can imagine this inclination to be different. So all the theories are different in this only. And the last thing we are going to consider is going to be which Carl Terzaghi has assumed that if the foundation is going to be at a given depth, that is the foundation depth df, capital DF now, so this particular zone of the surcharge is only giving surcharge to the earth pressure being generated, which is positive pressure now. So everything depends upon the actual calculation of positive earth pressure now. Mind you, this bearing capacity problem is actually earth pressure problem, which we really don't remember about this part of it, because today people always calculate the basic bearing capacity equation, forgetting the actual mode of action of this entire load bearing capacity. So this is of course a nice picture drawn by Professor Amit Prashant. He uses a slide for presentation on one of the short courses organized for structural engineers actually. I liked it, so I just put it back here. So what is it he is trying to do? He is exactly trying to show this, what is the different kind of things we are going to have. So people have neglected this now initially. Carl Terzaghi neglected the effect of the so-called surcharge, that means the thickness of the soil above the foundation level, and he said, okay, this is only going to contribute to the earth pressure here now, but he didn't imagine that this failure zone is extending to the ground level now. That is what is neglected by him now. So that is why it becomes effective overburden pressure, and he solved it for a general C5 soil now. And also important part of it is this angle of inclination here is taken as phi prime, you can say that now. So also it was taken for L by B ratio, the length by the ratio is large now, it's a plane strain problem. And of course, we assumed that the depth of foundation is less than or equal to B. And today, as I said, this may not be the case always, because even the code says up to 3 meters actually, we can assume the shallow foundation only. So long as foundation is going to be up to 3 meters below the ground level, we can imagine to be shallow foundation theory only. And I already mentioned the shear resistance of the soil up to depth is going to be neglected. And of course, he is assuming that the entire zone below the foundation is participating in the load distribution through formation of these limit conditions. And so the larger the zone, obviously, the more is bearing capacity. So there is a general shear failure because the entire soil around the depth and width is going to participate in the load distribution of the columns or of the foundation structure. And of course, the shear strength is governed by the Mohr-Coulomb criterion. So with this is the foundations now. What is it he has done? This is what I have repeated actually. So the same thing we have tried to do. The failure zone don't extend beyond the horizontal plane, and failure occurs by downward pressure exerted by the loads that I have mentioned now. So finally, what we are going to look at is we can just draw the equation for the load bearing capacity because we got two zones now. So we are talking of the vertical component of the earth pressure actually, which is going to be PP, the earth pressure, positive earth pressure into relevant angles actually, and then also the cohesion along the what you call conical portion actually, or wedge portion, and that is going to be the appropriate values will be after geometry is taken like this now. So we know that this AB, this length of AB, that means this side actually can be decided by the width of the foundation and as well as the angle which you are trying to pick up now. And so we put this equation for the load bearing capacity like this now. So what we are trying to load bearing is going to be for the total foundation. Now this PP value, which is positive pressure generated by this entire zone here now, is divided into three components. This is the most important significant contribution which Terzaghi made, which is followed by all other modes of theories. All of the theories now, whether it be Terzaghi, I mean, there's going to be Vasek or Balla or Hansen, everybody followed that. So this PP component, positive pressure component, is divided into three terms. One is PP gamma, which is only due to the rate of the shear zone ABEC, that means this entire zone ABEC, and then that means this entire zone which we are talking of here. Okay, And then PBC is the cohesion along this. Okay. And then PBQ. Q is always a term referring to surcharge. PBQ is the term referring to the surcharge here. Okay. So the partial pressure components are three actually, due to the weight of the zone and due to the cohesion and due to surcharge. So if you just put back those things here and then divide it to get the unit bearing capacity, divided by the ultimate bearing capacity, as you know, and divided by the width actually, then you find that we divide the same thing actually into same components, and finally you arrive at an equation which is simplified as, for mathematical purposes, as gamma b by 2 into n gamma plus CNC plus q and q. Okay, so now we realize that these values of NC and gamma and q are actually representing the partial pressure, and they are truly depend upon one, of course, the angle of friction of the soil below the foundation, and then also the geometry of the failure zone. Okay, and by the way they are determined, actually you find that they are obviously dimensionless actually. So the differences between different theories occur obviously because of the various shapes they assumed, shape of this entire zone and shape of this entire thing, angle here. Now people have assumed different values now. So Brown's actually, when Brown's has done a lot of work in this area, we're not going to use this equation directly, but Q ultimate is equal to QC for cohesion, and then QQ for overburden pressure, and Q gamma for unit weight of soil. So the same thing is represented in a different way. So this is what we have to see. There are three components for the bearing capacity, ultimate bearing capacity, and due to cohesion, due to overburden, and due to the weight of the soil. It's very important for us to note that there are equations like this now. These are of course simplified slightly, but then directly the NQ and gamma NC are functions of only phi actually. That is something, functions of phi, of course the shape also, but then here I'm just going the original equations, which obviously give you a feeling that why they are functions of phi only and the shape actually. Here is the Terzaghi's equations. The other things which we'll keep discussing very clearly is that you can always have a plot of these values of bearing capacity factors versus the angle of intersection or angle of shear distance we call it now. What is it we are going to find out? We find out that if you thought of the undrained case earlier, undrained case means only C is there, and so it is only C and C, and nothing else is there now. So you find that now both C and phi only, we find that this entire curve is going to come to picture now. When is going to the soil have both C and phi, effective C prime and phi prime? When the soil is actually over consolidated, which is very rare. If the soil is over consolidated, we'll have effective cohesion and effective friction also. So in those cases, the angle of friction will come to picture now. So the kind of range of these values are also given here. So most commonly for undrained case, it is this value which we are going to use, because the undrained case for normal constrained soils is always going to be having no phi at all, mind you this. This is going to be a very uncommon situation. Over constrained soil is an uncommon situation. We find that the surcharge parameter and Q, what is the value now? It starts with 1 actually. That means if the angle is going to be 0, this value is 1. That is where actually the bearing capacity factor, the bearing capacity for clays is not changed by the depth of the foundation as also by the width of the foundation. That is what we will realize, because coming directly from the general equation. And then of course we have this n gamma, and it starts with of course at this, and then it keeps rising so fast actually. We'll see this variation also. Mind you, here also log scale 1 to 10 and 10 to 100. So we find that this change is going to be very, very high. When once we got, suppose we are going to consider angle of 30 or something, that now see the range of increase is going to be so fast, because it's going to be on log scale actually. We'll see this. So this equation here is divided actually for a strip footing. We have seen that now. So for the strip footing now, we got same equation written in a better fashion now. We got effective stress conditions in this case shown. So C dash and C plus gamma df and NQ plus half B gamma and gamma. So we've seen what is the things now. And what Terzaghi suggested, of course, all of you know, he suggested values which are different. The coefficients here is different now for square footing and circular footing. So instead of 1 here now, he used 1.2 for both of them now. And here instead of 0.5, suggested 0.4 for square and circular footing. How do you suggest it? By just experience only. Based upon estimate results, he has actually done this kind of calculation. Obviously, today we know that they refer to the shape. We call them today shape factors. So shape factors introduced for first time. He didn't bother about eccentricity. He didn't bother about other things, no, but he did bother about the shape. Actually, he found that the equation earlier was not suitable for these square and circular footings. So he modified them as far as shape is concerned. So the most important aspect we should recognize is that not calculation of these things, which is very simple actually. But look at this now. The MC value, under in case we said 0, 5, and so it's 5.7, 5.14, depending on theory, it varies between 5.14, 5.9. It all depends upon that. This table is taken from Bowles actually. Okay. Now what is it we are going to talk about is, you just take it as 30 degrees angle now. For 30 degrees angle, obviously, the soil is going to be having both NQ and N gamma. So what is the value now? 22.5 and then 19.7. Now imagine that this angle is now actually for the soil 34. You determined correctly. What is the value change now? Total becomes 36.5, almost 50% improvement. And here it almost doubles, 19.7 to 36 now. That means every degree of change from 30 onwards is going to disproportionately increase the Berkovich factors. This is what is going to be most important to us. By assuming just 30 degrees now, by any kind of test, converting the SPT value into this and ultimate reporting 30 degrees now is meaningless, because each single angle, even if it's half a degree also, is going to improve the Berkovich factors significantly. This is what you have to realize clearly. And then you see that it becomes 35. Between 36, 34 and 35, what is the difference change? 36.5 to 41.4. 36 to 42.4. Just 1 degree made such a lot of difference. Imagine that the soil has got 40 degrees now. What is the value now? 81.3, 100.4. I mean, this applies more to compact soils also, not necessarily. So most of the embankments we are trying to do, if you are compacting better now, we are going to have, or even for a special case also, naturally we find that the values are going to be so high, 4 times, 22.5 to 81.3, 19.7 to in 5 times here now. So this is something we have to remember actually. Unless you determine the so-called friction values correctly, what we are going to give the results normally from most reports is going to be so conservative, because they would like to err on the wrong side. But by adding by 1 degree also, we are losing so much Berkovich factor values and magnitude. So this is what we have to remember actually. The second thing which have been brought out by BASIC actually much later is that we have seen the twin shear failure zones actually. Now that zone is actually totally taking up the entire soil actually into the limited equilibrium conditions, because perspiration is limited equilibrium condition now. He said this may not always occur. So there are 2 more conditions specified, that is local shear and punching shear. So what did he do, of course, is that general shear means actually we got the entire zone have the failure planes actually. But once local shear means, yes, this zone is not completely formed, this seems to be settling and only developing to just some nearby area, let us say, for these failure planes actually. And then, so in the case here, when it is going to be general shear failure, we find that there's a kind of peak value, and then it may reduce and may be constant. But here now, it seems to be settling disproportionately. We also have a case, punching shear, we will see later also in more detail, which is going to be very similar to this now. Maybe it actually completely goes down actually. It's not mobilizing anything on the neighborhood actually. So here also the failure could be, ultimate could be almost leading to failure now. So there are 3 conditions which is specified now. But for most purposes actually, this is the picture which is giving you this idea. But this idea is, of course, for demonstration of dense sand and medium sand and loose sand. So you see the loose sand kind of condition, very loose sand, by his model studies, he found that this is kind of behavior we are going to. Of course, for a dense sand, the behavior, as I have shown you earlier, was really perfect, local shear failure in the beginning, and then the general shear failure. So what is it you are trying to find is that, so these conditions are going to give you much lesser bearing capacity than the general shear failure, because the entire soil is not partially load bearing mechanism. Here, the entire soil is partially load bearing mechanism, because these failure zones are fully developed actually. Here, they are not developed, only restricted to this zone only, and here restricted to only this zone only. So this is the difference between the different footing tests he has done. Based upon this, he gave a theory. But today, actually, we consider both the local shear failure and punching failure as the same kind of condition. So as per our IS code and our understanding, we consider only general shear failure and local shear failure, which includes punching also, which means that the foundation is settling actually disproportionately without mobilizing the soil on either side completely. So that is what is specified actually by the SIC and followed by everybody else now. So for this condition, what he said was that we will not use the full value of C. So we actually use the value of C, which is only 2/3 of the C we calculated actually. We got in the laboratory. Same way now, the tan change the value for local or punching shear failure is only tan phi is equal to 2/3 tan phi. Phi is the main what we got by testing. And this is what we correction roughly is going to be 2/3 of this. So for loose sand and silt actually this condition. Now this is very generic also. It depends upon many kind of things now. What is suggested is something like this now. What you observed and what is suggested is like this now. That is, on this axis we got the relative density of sand, and then on this side we got the relative depth of foundation. That means D or B. D is the depth of the foundation, B is width of the foundation now. So what you find is that under these conditions, that means relative density high actually, and this depth of foundation is going to be, this ratio is going to be around 5. Probably these are all going to be general shear failure, and then local shear failure, and then of course in the zone here, when the relative density is very poor, naturally it's punching shear failure. So we are looking at this kind of estimates today. We don't talk of all of them now. We go to direct decision making actually. The other important thing, of course, is about the presence of water now. Now, water table can be anywhere when you conduct the test, because you may conduct the test as conveniently in summer. Water table is going to be quite deep, possibly, and then of course in monsoon time, water table may rise. So if water table is rising, actually there is a question of change in the effective, you can say, unit weight. That means, are we going to use the normal unit weight which you got now, the bulk unit weight, or are we going to use the submerged unit weight? This problem always going to come now. So in the beginning, what we have to remember, of course, is that Russell's equation is based upon the assumption that water table is located at a great depth actually. That is going to be very important for us to realize actually. So the correction for this is very easy for us. So what is it we're going to do? If you are going to have the water table very deep, let us say, that means, at a depth greater than the width of the foundation, naturally, no influence. Okay, if the water table is, let us say, around here, what do you mean by this now? This parameter which you are going to use for this soil actually will be different. That will be a submerged unit weight. And the parameter we are going to use for this, what parameter we are going to use for the soil above now? Surcharge. Surcharge is going to be same bulk unit weight. If the water table is going to be somewhere in between now, we will have to do adequate correction for this now. And that means we try to linearize it actually, assume some changes actually linearly. And but fundamentally what we are trying to do is that water table is so down at a depth equivalent to what you call as width of the foundation, naturally no limit at all. That means we are going to use the no correction for water table now. If the water table is at the foundation level, we are going to use obviously a submerged unit weight for the parameter we are going to use for that half gamma b gamma, and for the NQ naturally we are going to use the full weight actually. If the water table is going to be anywhere here or anywhere here in between, we are going to use linear interpretation in the density actually, which is given by the equations. I think these are the correction factors which we will have used actually. The other most important thing that's coming out of this is that what we got from these equations is what we call as the ultimate bearing capacity. Okay, so ultimate bearing capacity means it is the gross pressure at the base of the foundation at which soil face and shear. That means the pressure we can apply at the depth we are assuming. We are assuming only in the beginning, the depth is assumed initially. Minimum depth we know is 1 meter. So we are assuming that the foundation, let us say, is placed at 1 meter depth now. So what is the load we are going to place on this is what is going to be there. Obviously, this means that very clearly that this weight we are going to place on that is going to be including the weight of the soil actually, because we got a column and the neighborhood we are going to fill up with soil only. So first of all, we are going to consider the effect of that soil, that is overburden above the base of the foundation, is going to be including the ultimate bearing capacity. So net means what is additional load you can place actually, which means that from this ultimate bearing capacity QU, we are going to subtract the overburden pressure, gamma dF actually. So that is called QNU, ultimate net bearing capacity or net ultimate bearing capacity is the value. So then the safe value is going to come when you divide this ultimate bearing capacity by the factor of safety, assuming between 2 and 3. Okay, then what is the gross bearing capacity now? That means how much you can place now, naturally. Whatever we got out of this now, the net bearing capacity, plus this overburden pressure, which are going to be there. Now, this you have to be quite careful in what kind of foundation you are going to use. I'll come back on this issue later also. But right now, the gross bearing capacity means how much load you can place on this is given you by ultimate bearing capacity, net bearing capacity by factor of safety plus the surcharge you are going to have on the foundation. Now that is bearing capacity. The second part of it, which you are going to consider, of course, in tomorrow's lecture, more detailed, is the net safe settlement pressure. That means it's the pressure which the soil can carry without exceeding allowable settlement. So mind you, what is the parameter now in this case? The allowable settlement. The allowable settlement is, of course, decided by the courts, but also the final call on this is going to be made by the not only the court but also the client. That means the client can think, oh, I will not allow that much settlement as given by the court. I will be more stricter or more conservative. So it's between the client and the designer actually, but then within the limits of the codal practices. So what is the net allowable bearing pressure now? It is going to be naturally the smaller of the two. That is what it says actually. And the one thing we should remember is this value which you are going to get, considering both the net safe settlement pressure as well as the so-called bearing capacity, whatever terms you are going to use, that word for that has been misconstrued always. It says net allowable bearing pressure is the correct word actually. People also call as allowable soil pressure. But unfortunately, the code now they say allowable bearing capacity. All this is going to confusing now. What we mean is that we are going to give a pressure which you can place on this. People loosely call bearing capacity. Okay, but the moment you say capacity, it only means bearing capacity actually. That means as the ultimate divided by the factor of safety is going to net, and that's the end of the story, with and without considering the surcharge part of it. Now that I think is going to be taken consideration. But then the pressure word actually is going to come when you consider both of them now. So the code, of course, it doesn't use this term now, but we prefer to use the word actual allowable soil pressure, meaning that allowable soil pressure or net allowable bearing pressure, whatever terminology you do it. But then the word is actually the pressure and allowable. So if these two words are there, which means that both are considered, both settlement and capacity considered, that is our view actually, is it not? It's not bearing capacity, but the field engineers always say, let us know what is bearing capacity. And we also now know clearly, even from the earlier this one also, when we're calculating the ultimate bearing capacity, also what is it we are going to do? We calculate the ultimate bearing capacity by assuming a certain depth of foundation, assuming the different shape of the foundation, and then its size, the width and length and everything else. So there is no unique value for ultimate bearing capacity, so it depends upon the depth and width of the foundation. And if you are going to have different, let's say, widths now, what's going to happen now? The influence zone also is going to change. If width is going to more, obviously we are going to go down and find out what is the average value at least, or weighted average value of the phi value or C value. So this also has to be considered. It is not that we are going to use phi, same phi, and for different widths and depths we are going to calculate the bearing capacity. No, that is not going to be correct now. We have to consider the zone of influence of this particular foundation of a given size and shape. That is going to be important. So that means your so-called UBC, ultimate bearing capacity, is also not constant. It is, of course, a function of not only phi and the NC and gamma and Q, but also is a function of the shape and size and depth of the foundation. This is to be realized and had to be told to the client very clearly that this also depends upon the kind of structure we are going to have now. So coming back on the undrained condition now, we already said what is to be said now. So the value I said, sometimes we use the term, instead of CU, we use the term SU. So SU NC plus gamma D is what we are going to consider. And of course, the allowable value is going to be this parameter divided by the factor of safety and plus, of course, the core burden pressure, I mean, the depth of the foundation effect actually. So this is obtained, as I already mentioned, by the UCS or by the UU or by the field bench shear. So this is something we have to always keep in mind. Any one of them is going to give you the total stress parameters. And we already mentioned that phi is going to be 0 in most cases. And as I said now, there are people who have researchers who have got more experience also, more testing done also. And based upon their testing actually, they recommended that let us not limit this value of NC to 5.14 only. As it says now, it actually happens to be a function of the depth and depth of the width of the foundation now, and also depends upon the shape, square and strip actually. So this change is done actually. That means, I mentioned already that this value of NC can go up to 9. So the changes between 5.14 as initially suggested by Terzaghi, and then it can go up to 9 also as per this complex corrections which is usually followed. And for a drain condition, obviously sand is high permeability, we can always take it as whatever we got FHS channels only. And if it is going to be clay condition now, we already mentioned that for normally considered clays now, the C value is going to be 0. And of course, phi is going to be there. And otherwise, sands, we are going to conduct a axial test. Of course, easier to conduct a direct shear test. And then, of course, from the SPD values, we can also get the bearing capacity factors directly or indirectly. That means from the SPD values, we can use the correlation between SPT and the angle of friction. And then from the angle of friction, we can, of course, derive the NC and gamma Q based upon the theory we are going to use now. So what was first done actually? This was first done by Peck, Hansen, Thorburn, 1974, almost now 45 years ago, but people consider it valid only. And then that is given now, depending upon n value. This is called for n value and the friction actually. This is basic curve. Okay, this is basic curve defining the value of SPT and giving us the friction angle actually. Okay, now based upon the SPT, the soil also has been divided into different zones now, very dense, medium, and loose, and very loose actually. Then of course, from this curve now, we can also give this get this value of NC and gamma and Q now. That means from this n value which you got now, and we can always go down and then get the values of NC and gamma and Q, or of course, anyway you think actually. That means if you are going to here, of course you go up now to meet these curves and then interpret directly NC and gamma and Q directly from the SPD values, obviously corrected for all the necessary corrections. This also is recommended by IS 6003. We will come to that when you see the actual drawing from the code. So this is one convenient way, particularly varied only for sandy soils, wherein you can enter, we can directly get from the corrected SPD value the values of bearing capacity factors, NC and gamma and Q now. Now we can also look at the various series as I mentioned now. If you calculate the Terzaghi's bearing capacity factors, N gamma, NC, and Q, N gamma, NC, and Q, all the three of them actually, as a function of the angle of friction. Naturally, the Terzaghi values for general shear failure fall like this. And if you calculate for local shear, these values fall like this now. Meyerhof has used some assumptions, we'll come to that. And his values actually are lower than Terzaghi, but slightly lower than that recommended by Terzaghi, because I mentioned already the assumptions the Meyerhof made were slightly different. Meyerhof basic and all made was slightly different, and that's why the small change is there. So once you look at that now, it's too small, but you can also get copies of all of them now from Bouth's book actually, the page from that. So we got Terzaghi's 43 method, we got Meyerhof method, we got Hansen method, and we got Wace's method. So you find that actually basic is the first one probably, and along with Hansen, we find that the Meyerhof values and the basic values are somewhat similar. That NQ and gamma is NC is very similar, and gamma is different now. So you find that out of all of them now, the Hansen values actually are considering various factors actually, which we now call as shear factor, inclination factor, and depth factor now. So instead of using different kind of you can say terminology now, for the most general case now, Hansen has given us the various kinds of factors in one go actually. That is the advantage basically. Okay, so when once you look at this methodology, what is it which is going to come out is that we already mentioned here now, we have the same kind of foundation now, what we thought earlier. So what was it which is done by Terzaghi? Of course, we have seen that now. If you see the left-hand side of this now, he considered the surcharge effect only as giving rise to the earth pressure actually. The pass pressure we are going to calculate is also adding on the effect of the surcharge now. The failure zone obviously doesn't extend into that now. Whereas there are some theories which have taken actually that this entire thing is going to be part of this, but in trying to do that now, the failure zone is extended into this now like this. So this is the total failure zone now. So Meyerhof has got like this. So for Hansen Meyerhof now, alpha. What is alpha now? Alpha is inclination now. If you consider Terzaghi, I already mentioned this alpha value is actually equal to 5, whereas Meyerhof has assumed 45 plus 5 into. Okay, in the same way, this value has been defined by different ways actually. I will not want to get details of this. This picture is available in Bouth's book also. So all these variations are going to get now depending upon the shape of this now, depending upon the failure zone we're imagining now, depending upon the active zone which I have defined, and is it optimized or not, is all the changes are there now. So by this process now, we can get actually the factors, as I said, started with Meyerhof and basic now, and shape, depth and inclination now. And the advantage we got in trying to do the generalized solution by Hansen is not that we like him, but not only he has given us the shape factors, depth factors, and inclination factors, of course, the function of the shape and size of the size of the what you call foundation, but more importantly, all of them are functions of phi. But then he's also given us the ground factors, also given us base factors. That means I mentioned already, we're also always imagining that the base of the foundation is horizontal, level. Now, it may not happen in certain conditions of, let us say, industrial structures, the foundation needs to be tilted also. So that's one case. And in all the cases, the ground is not horizontal. It may also be inclined. So this inclination of the ground is considered and inclination of the base is considered. So there are equations which are simple equations which are given to us now for the shape, for the depth, and for the inclination, and also for the ground inclination and for the base inclination. That's why they become the most generic kind of factors which are going to do. We'll spend a minute actually in what is the difference between these series now. So we find that the value of NC and NQ actually, the value of NC and Q are the same for all the three methods. What are three methods now? Meyerhof, Hansen, and basic. Hansen is what we are proposing to use anyway. So Meyerhof and basic values are similar to Hansen's equation. Okay, so this is what is mentioned here now. NC and Q are functions of phi. If you look at N gamma by Hansen and N gamma by also Meyerhof and N gamma by basic, that means V for basic and M for Meyerhof and H for Hansen. So what is coming out is, let us imagine again the common parallels 30 degrees. For 30 degrees now, the value of N gamma by Hansen is going to be 15.1. The value by Meyerhof is 15.7. The value by basic is going to be 22.4. Okay. Let us go higher, 34 degrees. So the value by Hansen is 28.7 and this by 31.1 and this is 41 now. So what is it we are actually choosing? Hansen obviously is going to be quite conservative. That means it gives us lesser values actually. So that is one reason why people preferred the Hansen, one of the reasons. And also, as I told you, he gave us the various kinds of factors for all possible applications now. So this is what I mentioned in the same thing now. So what he did, he is actually factors SC, DC, and IC. SC, DC, and IC actually, what does it mean? They are shape factors actually. Okay, SC, SQ, and S gamma are the shape factors. Are shape factors for cohesion bearing factor, for surcharge bearing factor, and for the zone actually. So in the same way now, he defined DC, DQ, DF, and D gamma as depth factors. And then IC, IQ, I gamma are inclination factors. So these factors are actually meant to correct the value of the bearing factors, basic factors now. So these are in addition to the values which you got from the table I've shown you, the NC and gamma NQ. So we use them now. So for each terminology now, we got shape factor, we got depth factor, we got inclination factor now, related to all these things now. So these, how to determine, I have given you the equation earlier, and also they are given the corrections for inclination. So this kind of thing. And as I told you, this inclination is given now. This eccentric loading is given here. Indirectly, it means inclined load only. And we, in the IS 6403, adopted the same general format. That is something good for us. So the more generic, but then the IS code has given its own bearing factors actually. So let's not get into comparison. I just give the comparison earlier to understand the differences actually between the various series now. Okay, so we are back to the same basic equation. Basic equation meant as equation because the format of the equation is what we are using. Now we are correcting for these factors, the shape, the depth, and inclination for each one of the three bearing factors now. And of course, we know that what we do for slopes now, I have mentioned earlier, we will not have much time to get into this, but I will do other things now. The other important point I want to cover, of course, is that we said the soil is going to bulge when once it's almost near failure, when all the failure is, the entire soil is mobilizing its own capacity. So what is going to be the effect of the outward movement actually. The bulging you find on the top of the ground actually, the ground surface. So that is given by two factors. One, of course, what is the extent up to which this is going to come out now? F is the extent to which is going to come out. And depth is the depth of this failure zone actually. D is the failure zone here, small d, and F is the zone of influence of this failure zone, which is seen outside actually. Okay, so you find that is a function of angle of intersection. And what is it you find now? F over B is a function of angle of friction now. You see that for 30 degrees now, what is the value of F over B? It is 3. That means it is going to be influenced by 3 times the width of the foundation. Up to that, 3 times this side, 3 times that side now. And if the angle of friction is going to more, let us say 35 degrees now, this value becomes 4. If the angle of inclination, angle of friction is going to 40 degrees, this goes up to 5 also. So 5 times the width of the foundation is influenced by the foundation soil actually. So if it is angle of friction is going to be low, maybe 3 times only. If it is much lower, it's going to 2. So you always feel that the zone of influence is going to be increasing in size. And because increasing in size only, the bend capacity is improving now. So both are related now. So our, people always say doing model test and feel this one also, even for Plato test also, oh, we use the 5 times the width actually. No, that's not necessary. That's not correct. That is only correct in, so 5 times means 2.5 times, that means 2.5 is somewhere here now. So that means the angle of friction is 25 degrees. If you got angle of friction of 30 degrees now, it should be 3 times, 3 plus 3 plus 3, 6 actually, which we are not following now. So I wanted to show this influence to you. What about the depth of influence now? The depth of influence also is going to be changing. And let us say for 30 degrees now, depth of influence only 1. That means it's only 1 width of the foundation. If it is going to be 35 degrees now, we find that this value may become 1.3. That means more depth is influenced actually. If it is going to be 40 degrees now, it is nearing 2 actually. That means twice the depth of the foundation, twice the width of the foundation influence up to the depth actually. So both in the depth and the zone of influence, the angle of friction is got very serious support actually, or serious now. So again, these are generalities you find in different books in different ways now, but we have to follow essentially the code. So I will not get much of them, but you should use some of the most advanced books to understand which theory is going to be better for you for predicting the correct reason. But before going to that now, there's an excellent table actually given, summarized by again Professor Bowles. And what he has done is he has actually collected experimental data on model tests, model footings by Milovic and by Moore actually. So the data is given here. That means Milovic has done, of course, for this kind of situation. That means, say, 4 of Moore and 4 of Milovic now. So the dimensions he has given now, depth and width and length, and of course gamma, phi, C is given for all these 8 tests actually. You see that the phi value is changing from 37 degrees to 30 degrees here. The phi value here is varying from 20, 20, 20, 25, and C value is rather small, and C value also could be varying now. So there is a lot of variation in these tests actually. And so both, he has given the ultimate value which you got by the laboratory test now. What he did also is, he himself compared actually from these data which you got here regarding the depth, width, and length, and gamma phi C actually, he predicted what is the value which are going to get ultimate bend capacity by Desargues method, by Meyerhof method, by Hansen method, by Basic method, and Ballas method also. So when he tried to do that, what is it we are going to get now? We find that, supposing we take this case now, we find that Desargues method is 9.4, Meyerhof is 8.2, Hansen 7.2, and 8.1, 14 here now. So what we find? We find that the Hansen's value is most conservative. In the second case of test now, and this is actually value is much lower than what we got in the field, in the model test actually. So model test is 10.8, so probably it's lesser than 14 actually, but more than in Desargues value. What about the second test now? The second test, let us say, the least value is given by Desargues now, 9.2. Okay, 9.2, 10.3, 9.8, 10.4, 15.3, and most results are 12.2. So again, is higher than least predicted actually. And no result compares with this. Again, of course, it's lower than that by Balla, but none of these values predict actually correctly. Same thing happens to 24.2, the third test now. And here, probably, it is in same range at least. And for the fourth test, it is again 933. And only Balas predicts correctly, exactly. But with some assumptions anyway, 24.7, 23.4, 28.4, 19.7. So what is it you find is that in these cases, it appears that the values are actually more than what we observed. In other cases now, it may not be always the case. It's 4.1 here in middle test now for these C5 soils actually. And this 4.3, 4.8, so least predicted is 4.3. Okay, here the least predicted is 6.5 and it's 5.5 here now. So you have to go back and study this page actually given from the Gauss book only. What is the result of all of them is that none of theory is actually able to predict what is the value. So there are variations in the predictions also. They will not compare necessarily with the actual model values, and these are still model only. In the real case now, there will always some variation. And so it's very difficult for us to say that this theory is the best and the other theory is not correct. So this is mentioned very clearly in the opening statement by IS 6403. I thought I will put it for your observation. The bearing capacity of foundations is needed for dimensioning the foundation of any structure. Several methods are available for the determination of bearing capacity of shallow foundations, and this standard gives some of the methods which are commonly used for the purpose. Comparison of the results shows that when each of the various methods is applied to different problems, no one method consistently gives higher or lower values of allowable bearing pressure. The designer must therefore regard the methods as aids to design, which cannot replace the critical role of engineering judgment. I think we ignore this. We always say that the standard has to be applied mechanically, but the standard itself says that no one method is necessarily correct actually. So unless we're able to see that the field condition is going to be synonymous to the theory which are going to use, so sticking to the code itself is not necessarily at all actually. This is what is said. Comparison results shows that when each of the various methods applied to different problems, no one method consistently gives higher or lower values. This is very critical statement. Designer must therefore regard the methods as aids to design. They have not given the final verdict that you have to use this method. So please keep it in mind. So the rest of it is following, of course, very clearly for sandy soils. And actually, we just see the same equation we already thought now, including local shear failure, whatever we discussed, the same thing is there. And then, of course, the factors he has given actually are not necessarily following these methods, but then because IS code has given us, we are going to follow these methods only. Okay. So for our application, we are just going to use the bearing factors as given in the IS 6403. Then, of course, for other, that is for strict foundation, again, they now say that it's actually Hansen. They refer to the factors SC, SBCIC, that means shear factors, depth factor, inclination factor, in the same way as they refer to both for general and local shear failure. And then, of course, the factors they have given, actually, these are called as simplified factors from Hansen series. One is the detailed factors, and the simple factors. Today, we can always develop a Excel sheet actually to get all these things now. Most consultants do this. And so the depth factors, there's a shear factor, there are depth factors for DC, DQ, D gamma. And so naturally, inclination factors are also there. I gamma is different, but other two are actually going to be the same only. So inclination factor now. And I already mentioned about a footward table. This is consistent with what we proposed earlier. And then for corrosion-less soil now, obviously, which is going to be taken into consideration. So that is given actually as a kind of aid to us now. So we say that relative density greater than 70%, less than 20%, and 20 to 70%. So void ratio, they give inclination less than 0.55 and then greater than 0.75 and then between 0.5 to 0.75. So we define this as dense condition and loose condition and medium dense condition. So when the relative density is more than 70, void ratio less than 0.55, we take it as dense and then take it as general shear failure. And worst condition now, we take it as loose sand and then apply for local shear, also as punching shear actually. And if it is between these two, 0.55 to 7.75 or 70 and 20% relative density, naturally we interpolate. So that is the recommendation by the code. And then, of course, further what we are going to do, we can use the SPT values directly, as I said, by the curves which are given now. And the other codes give you also to correct these SPT values, both for overburden pressure and also for naturally reactancy. So these are of course known. And naturally, we are going to use a slightly different kind of thing. What is important for us to realize is that overburden pressure correction actually is very high at the top, near the top. Why it is so high at the top now? The value goes to almost 2. The correction value is 2 actually. That means twice the measured value we are going to get for corrected value for overburden. Obviously, when it is going to be essential, this value for sand only. For granular soils, what is going to happen now? At the top, the confinement is less now. As you keep going down now, the confinement is there because of overburden pressure now. So when it goes to certain depth now, yes, the influence is felt maximum, and below that, we're not going to find anything else. So near the surface, there's no confinement, so value is going to be, the value correction factor is going to be 2. And then as you keep going down, naturally, the correction factor becomes ultimately nothing actually. So that is what we have to remember. The correction factor is again very normal. So that is fundamentally we have to remember this. And there are equations giving this now. Depth correction, you know very well, nothing to say on that. Applicable when it's below water table, fine sand and silts actually, we apply this correction. And what we are trying to do, any value more than 15, we are going to reduce by half. That part of it we are going to do by half. So whatever curves are given you for relating the SPT value with 5, the same thing is given here also. As suppose just 3. Earlier I gave the combined result for NCNV1Q also. This just gives you the curves actually. Directly we can use it now. So then for coastal soils, again the same thing, CNC, and we are using the CNC values 5.14 and the factors as defined earlier by Hansen and given in the code. And if the soil is, you can say, layered or homogeneous, not homogeneous, so naturally we are going to take the, I should say, weighted average now. And so long as the values don't differ by more than 50%, we use this weighted average actually up to 2/3 of the depth up to 2/3 of the width of the foundation. So that is one thing we can try to do. And of course, if the is only 2-layer system now, we got the corrections actually as the corrections for the weighted factor in terms of C2 by C1. C2 is the bottom layer, C1 is the top layer. And you should remember that this value here is incorrect actually. You should replace by C2 by C1. There's a mistake and it's agreed by the code also. And so this is also a function of the D by B. So we should see that actually the value is 1.4 when the C2 by C1 is equal to 1 only. That we know very well. And then of course with the higher value of C2 by C1 or lower value, we correct it also according to the D by B. So that is the questions again. And I think this is going to look actually both twice since we are going to do it now. Very clearly heard, it could be single eccentricity one side or eccentricity on both sides. So that means both length and width side. We do in a standard fashion, which is accepted actually. So terminology which I said is already there actually, except that they talk as allowable bearing capacity. So this is where the terminology we differ. The net intensity of loading, which the foundation will carry without undergoing settlement in excess of the permissible values for the structure under consideration, but not exceeding the net shear bearing capacity. So the terminology which I used earlier was same, except that this word we suggested is going to be not capacity but pressure, because capacity somehow mentally people think bearing capacity only, devoid of the settlement aspect. So if you use this terminology, it's going to be good actually, but anyway, the code uses terminology. So this is what we said eccentricity. So we know very well that if it's eccentric in both sides, what is important for us is that we are going to lose all this area. This area is not considered for determining the actual load bearing capacity by this methodology. So this becomes a waste, but this is required from structural considerations, and that is what is going to be important for us. Okay, so finally, the so-called allowable bearing capacity. So-called allowable bearing capacity, as I said, we wanted to call as bearing pressure, is the net admitted bearing capacity as obtained earlier, divided by total factor of safety, that becomes net shear bearing capacity. And then the net soil pressure, we already use the terminology now, shall be taken as either of the following, whichever is less. So that is exactly what we decided. And that becomes now the safe bearing pressure or allowable bearing capacity. So we should consider all of them now appropriately and use the other codes also. So finally, from the foundation design viewpoint now, what we find actually is, this is very general observation. For clay, the so-called allowable dissolved bearing pressure depends both on bearing capacity and settlement. I mean, it's very difficult to say that it's a function of bearing capacity or the function of settlement only. It depends on many aspects of the consolidation behavior, of the strength behavior of the clay. And of course, there's going to be over-consolidated and consolidated, on which aspects we will discuss more in detail when you go to settlement. Then for sand, actually, probably the settlement governs more. Though the settlement is going to be immediate, so we don't consider that and we take it as a only bearing capacity issue. But then actually settlement governs, because immediate settlement is going to occur is going to be more. But then it happens during construction, so we are not so much worried about that. So it becomes primarily a function of only phi, and of course it says size and shape, and but settlement theoretically governs usually. So that is with the thought now. We will actually move to the next step of determining the so-called allowable bearing pressure, and that we will consider in the tomorrow's session. So at this juncture, have you got any fundamental doubts? Karthikeyan?
Yes, sir. Can you hear me?
You have got some more doubts?
Yes, sir. Actually, two things. The triaxial, when you mentioned triaxial consolidation untrained and consolidation trained, you mentioned the consolidation untrained or R method. Or,
yeah, that's good terminology. That's the terminology only. Now we don't use that. People days they used to use it now. So don't worry about that. We call CU or CU bar now. Console and drain test without pore pressure measurement. CU bar means with pore pressure measurement.
Yeah, that okay, sir. R and S I didn't know, that's very okay, sir.
Yeah, that is a good terminology actually. S means slow, R means rapid.
Yeah. Okay.
It was good terminology, so don't get into that because we are considering this one. So just one slide I want to show also. This is a project we have done at Gangavaram Port in Vizag actually. Of course, in approach the bridge basically. But the point we are trying to say is that this soil profile is realistic. If you are going to have this building, let us say 100-meter long building, if you are going to construct a school or college or some kind of functional hall, actually, large functional halls, we find that it is going to be based upon maybe is this kind of strata or this kind of strata, this kind of strata. So there will be now a lot of different settlements occurring out of this. Total settlement, different settlement, and which is varying with the time also is going to be an issue. And of course, bearing capacity is an issue. And then if you are able to see this actually, you're able to see this also, for different depths, the soil is different actually. That means this soil is black on soil actually. If it's a bridge approach again, yes, we got a good material at 24, 25 meters now. And in between there are layers of this sand. It's all otherwise clay, soft clay actually, if you are able to see this slide. So the point I'm trying to say is that now it becomes very difficult for us to have foundations. We don't mean only foundations of buildings, but we also mean foundations of embankments also, foundations of sedimentary structures. Of course, we'll emphasize on this when you towards the last lecture at the end of your near end of your program. But thing is that this variability in the soil and the structure both are going to be together now. For an embankment, obviously, as an embankment, there's more tolerance, isn't it? For a building, there's less tolerance. And there are cases when the buildings are settled also, as much as 1 floor. But nothing happened to the building as such. It happens, it depends, connection, things like that now. So the issues are always based upon the type of structure we are going to make and utilitarian function of this now, and tolerance level and the aesthetics, and of course on the basic foundations which we are going to design. So this is going to be critical for us to understand. And I just want to repeat statement I made now. This is not simply inputting some test results into some equations. That's where we stand by whatever I mentioned, Professor Madhav quotes always. Foundation engineering is an art ultimately. We have to play between all these variables to be a successful designer. And this goes actually with your own fundamentals and also observations around of the soil and the behavior of the structures. And unless until we do it now, you can't bring these equations or my PPT into the classroom. Some of you said, please give me PPT. A PPT is made by us, by us individually. It is not simply cut paste from the book actually. I had experience in 2-3 different institutions in the state also. and the authorities ask them to make a PPT. So they simply cut paste actually from the book and then say, this is my PPT. That is not PPT. The equations are there anyway. Anybody can read it now. But what more you're going to bring to the equations? How to get the background of that now? And this is the purpose of my presentation always, that yes, you can always read the equations and fill up the gaps and fill up. It's not an assignment. It's not tutorial. What you're teaching is not tutorial exercise. Somehow the emphasis examination also is becoming tutorial kind of thing only. Just fill in the this ones, convert the units and things like that now. And that means they're not getting the hang of the foundations actually. You teach advanced methods, but still don't know how the behavior of the soil is going to be there. So teaching all the 5 methods actually is important, maybe at PG level to understand, maybe do research on that now. Is it required today for practice by engineers? That is the crux of the entire issue. Okay. Any other doubts by anybody?
So good morning, sir.
Good morning.
Sir, in one of your slides, you've been showing the difference in N-gamma values obtained from Basic, Hansen, and Meyerhof theories.
Yeah.
Both Basic and Hansen also assume the same angle of inclination as 45 plus 5 by 2. But still there is a difference in the values of N-gamma. Can you explain us?
What about other assumptions now? What about the shape?
Okay.
Many things are there, no? That's why I said always remember. It depends upon 3 things actually. So 3 things are varying in this now. I have done not area. But the point we are going to make is now, the values are different because of the assumptions we made now, which I have shown you. There are 3 different assumptions they made now, and they got all these results actually. And today, for you to teach or for you to practice, these are not relevant now. If you want to research in the area, yes, you need to do research. Okay, but if you are only teaching UG or PG students, we have to only see what they have done. That is the main thing now. And also probably for research level now, all the theories are going to be good for us to foundation of black on soil. Or for us to think on sills actually. Isn't it? Or are the theories to be modified further when you got different structures? Or when you think of coastal erosion. So those things are becoming practical. We are doing a lot of work on hill areas now. Okay, I've shown you 2 slides. I skipped over that now because I think indirectly Professor Keshav may be showing more in detail of the foundation slopes also on rocks actually. The point I'm trying to mention is that they are becoming more relevant for research also. Not what is the difference between Basic and Smashman or Basic and Meyerhof and all. Hey, they are there for us to understand that these values are different and yet none of them can actually predict what is happening in the field. You can also do the same thing now. For example, you can always get many load tests done, very commonly common project for all the UG students by almost all universities or all colleges. But do they get reliable methods now? Or the tests are relevant to this now? That's why I've shown you the value of F and D actually, the depth of the zone of influence and the width of the zone of influence from the plan level actually. No, that is not being followed. What about friction on the sides now? So the point is that when you're teaching now, these aspects need attention, great attention, not just merely replacing this and with that and things like this. Unless you have more fundamental clearly, even your projects which are going to are meaningless. And also, quite a few people are trying to, instead of understanding the basics now, they use only some computer-based, actually Excel sheets and maybe Plex and things like that, without understanding what is the basis for this now. That is what I try to give you that. Okay, if you understand the basis now, obviously when I choose parameters for practice also, or for any Excel sheet, naturally they need to be realistic. They need to be realistic. For example, tomorrow we are going to do a structural design for this now. What's models what you are going to get now? Is it sufficient for us to conduct a Pareto test and then say that the modulus I'm going to get now? Or is it possible for us to convert the SPD values into modulus now? So they are the practical problems for practical engineer actually. Isn't it? So now people still think that I have skipped completely Pareto test because of the possible mistakes which are using in interpretation of that. You see, this I not spent any time on that. I didn't even mention the test because what is being done is meaningless. And because the code gives you that and we teach it also. There's nothing wrong in teaching it. But the point is that now, how many of these tests are meaningful in relation to just the size of the foundation, vis-a-vis the size of the plate which you are going to use actually. Okay, so you ought to understand the basics first of all, then appreciate what are the limitations of the code actually, and then of course what is the area we are going to pick up for your own project work. I'm not saying thesis work. dissertation work in MTech or BTech project work actually, which is going to influence now. And most students are interested in doing some calculations and doing some software, and then without getting into understanding of what does it means actually by saying these changes are occurring. That means the feel of that is not happening. That is what is causing the distress in the foundations, in the structures. And I said in the beginning itself, there is sort of what we call as time overruns and cost overruns. And it's, the amount of money which you are spending is about 2 lakh crore is wasted on this time overruns because of geological surprises. Can you imagine this now? That means making economic structures, making safe structures is making good investigation is in your hands. Because a lot of consultants or government departments come to you for doing testing. That means they assume that you know everything actually. But what is being done is, yes, you do some mechanical testing, you simply put in these equations and say, okay, my job is done. What I'm saying is that the job is just started because you still don't have anything at all. Quite a few of the consultants actually, what are regional consultants, they are getting drilling by a boring fellow actually. They go to university or they just give to this, dump the sample somebody else. So the client is totally unaware of it. Are we supervising the field work actually? Is the hammer standard? Is the storage of the sample proper? Is bagging of the proper? No. Many things are there actually, which you can't teach it because investigation is a subject which you teach normally MTech as a full course at half a course. That means at 20 to 40 lectures. Now the foundations course, you know very well, is also a course for 1 semester. So in a development program now, we are trying to give an overview of that now and bring out the facets of what made these kind of decisions of practice and what are limitations and what you should have to do as a practice engineer, as a teacher also. And that is the emphasis I always try to give. Maybe I have partly succeeded, but a lot of things are missing also because of the limitations of time and exposure and your varied background also. For example, Karthikeyan, you're a master's in geology. Naturally, his appreciation of soils is limited, maybe more in terms of rock mechanics. No doubt on that now. So where each one of us have to fill up these gaps actually in understanding, in knowing the soil around. I think I always go with principle. No, I'm going to propagate this. You have to know your KYS actually. If you don't know the soil all around you, what is it you're practicing actually? If you're not tested the soil around you, what is it you're trying to do? That's the way, that's my approach from the beginning and it continues to be there. Okay then, thank you very much. Any doubts you got, you can put in your chat box. I can reply today or tomorrow. Thank you, sir. Over to Professor Edgar.
Sir, thank you very much, sir, for detailed lecture on bearing capacity theories. And you have clearly brought out the merits and demerits of each of the theories. As rightly pointed out by showing a statement from IS code. So the engineer who is making an estimate of bearing capacity should know, should understand the limitations of each of the methods and whatever value is adopting, right? He should use his own engineering judgment, that is right. So just like now that for COVID, we have availability of several vaccines. So even doctor, if you go to doctor and ask which vaccine I should take without much complications. So it is a difficult task. Just like that, in bearing capacity estimation also, a lot of engineering judgment is required. So only a person who is really well experienced in that and has sound knowledge in geotechnical engineering will be able to give a proper advice. Not only that, as Sar was pointing out, particularly in granular soils when phi value is more than 30 degrees, right? The change in bearing capacity factors, particularly N gamma and NQ, right? For each degree of increase, right? They are increasing significantly. So that's why proper estimation of angle of imperfection is required. So unfortunately, most of the laboratories we have direct shear box apparatus with specimen accommodation facility for 60 by 60 by 20. So wherein in case of gravelly soil, they will not be able to properly test and arrive at phi value. So there also there is need for testing the specimens either in direct shear test or triaxial test using larger size specimens to arrive at an exact value of 5. So not only bearing capacity which we are estimating depends on the method which we are taking. Obviously in India we feel like going for the method, right, or equation given by IS code, but the input parameters of soil shear parameters C and 5, right, how you are determining, right, and the person who is testing, right, all these things play a vital role. So SAR has clearly brought out the difference between safe bearing capacity, safe bearing pressure, and allowable bearing pressure, right? So in design you have to use allowable soil pressure. Even other speaker, right, was referring, and in most of the books you find it as allowable bearing capacity. Even IS code says allowable bearing capacity, but capacity means it is right maximum pressure a soil can bear. So soil, SAR was mentioning, it should be right to point out it has allowable soil pressure, right? So in design you have to use that parameter which ensures safety against risks from shear failure as well as settlement failure. So thank you very much, sir, for your excellent presentation. I think participants got clarified about all the doubts, whatever they have on bearing capacity. I can see from chat box. There is a big appreciation for your lecture, sir. Thank you very much, sir.
Thank you. Ravi, I will reply to your question tomorrow. Ravi Kiran Nanjala. I will reply to you tomorrow. Okay? Today I think we already is the time. Thank you. Thank you for the opportunity.
Sir. Thank you all the participants for your participation in the morning session and for right enriching your knowledge in the area of bearing capacity of soils. So thank you all. We'll meet again at 4 p.m. for the second lecture of the day. So thank you all. Have a good day.
Thank you.
Thank you, sir.